webinar. My name is Julien Mas from Erasmus University, and today with Professor Geiger, it is our great pleasure to welcome Professor Insa Neuweiler. Professor Neuweiler is a professor of fluid mechanics and environmental physics in civil engineering at University of Hannover. She holds several diplomas in physics and environmental sciences, including a PhD from ETH Zurich, where she worked on macroscopic parameters for two-phase flow. She then did a postdoc at Imperial College London before moving to University of Stuttgart, where she led her own research group focused on upscaling flow and transport processes in porous media. It is during that time that she wrote one of the most defining papers on homogenization of permeability fields, published in Water Resource Research in 2008. She moved to University of Hannover, where she remains today. On behalf of the Geoscience and Geoenergy webinar team, I would like to thank you, Professor Neuweiler, for accepting the invitation. The floor is yours.
Okay, thank you very much, and thank you for the invitation to this nice seminar series that you put together here. Before I start, I would like to acknowledge the people whose work I'm going to present. Most important, Natascha Brandhorst. I'm going to show a lot of her work here in this presentation. And I'm going to present now something on modeling of flow processes in the unsaturated zone with application in data assimilation. So I switched the topic or the title. I dropped the transport, and I would like to talk about modeling in the framework of data assimilation. Before I start to talk about modeling, I would like to say some words about why do we want to model unsaturated flow? What is the unsaturated zone? Although I guess that's known to everybody, but some words about that. And now I'm stuck here. So that's the unsaturated zone. It's a hydro system in the subsurface. And if you wish, it's the layer that is sandwiched in between the atmosphere and underlying groundwater bodies. It's rather thin, several meters depth typically, and you have the flow of air and water in this system. It's an inhibited in a system where animals live and plants grow, and that causes certain structures. So if we look into soils, they are very heterogeneous. Typically, what they have is a layering structure. This is because how they are generated, and you see here these typical crack-like patterns. This is also because of what's happening inside. And why is it such an important system from a water perspective? It's, of course, very important because of the water balance. How the incoming water is rainfall is divided into recharge in the subsurface and what goes back into the atmosphere, what goes into the rivers. That depends strongly on what happens in the unsaturated zone. But it's not only the water balance, it's also the energy balance that is directly related to that. That's important from an atmospheric perspective. And for example, latent heat flow depends a lot on the water availability, so on the flow processes in the soil. It's also important for component transport, most prominently, of course, greenhouse gases, where it can be a sink or a source, but also, of course, the vadose zone or the unsaturated zone is very often considered in relation to agriculture or food production, and then it's transport of nutrients, but also pesticides as an example. So there are a lot of important processes that happen there, and for this reason, we want to be able to predict them and we want to model them or understand them. And how we model, as always when we model, depends on the questions that we have. And here, related to that strongly, is also the question on what length scales do we look at the system. And very often, we look with a smaller scale perspective. An example is if we are interested in agricultural applications. For example, if we are in arid areas and we do drip irrigation, or we are after pesticide transport or nutrient transport, we really need to see or understand the details, how water is transported to the roots of the pesticides, how much really gets to the plants, how much is getting into the water or into the air. and then we really look at a smaller length scale. However, there are also a lot of questions where we look on a much larger length scale on the system. And I chose here one example because this is something that we have a lot talk about a lot in Germany, and this is droughts, because we are having droughts in the last years quite a bit, and it's clear that we will have a lot more of this in the future. And so we have to deal with the situation. And one measure is to at least be informed. So one wants to have a monitoring system, for example. And here's a quite famous one. This is from the Helmholtz Center for Environmental Research. And you see here you can get the state of the soils in the uppermost 25 centimeters of the whole of Germany. I should say this system does not use the type of models I'm talking about, but nevertheless. Yeah? So this is maybe information we want to have. And here the size is really large, the whole of Germany. It doesn't have to be that big. We might be after a monitoring system for groundwater recharge, or we just really want to predict evapotranspiration in a land surface model because that's related to weather prediction. But in any way, the perspective is then really that we are looking, let's say, at a small catchment, and then the unsaturated zone is really this layer, and we are interested in the fluxes that go in and out. And this is the perspective I would like to take here. Okay, and so this is the structure of the talk I'm going to give about this. First, I want to say something about the models that we use, the flow model, and in particular the parameters that we have here. Then I would like to talk about how we deal with these models in relation to data assimilation. So first I will say something about data assimilation for flow in the unsaturated zone, what I mean with this, and then come to the question that we are thinking a lot about, and this is how to deal with the uncertainty and the heterogeneity that we have. Okay, but first about the models. So the standard model to describe flow in the unsaturated zone is the Richards equation. Again, I guess this is known. This is what you would get if you have a two-phase flow model, because we have two-phase flow, water and air. If you say one of the fluids is infinitely mobile, so the viscosity is zero, this is what you would get. So this is the Richards equation. It's a mass balance. It says the change of mass with time, and mass is here represented by the water content or saturation, if you wish, equals the divergence of a flux, and the flux is a Darcy flux. So it has two parameters, and one is the water content and the other is the hydraulic conductivity. And the variable is the pressure head, which is negative in soils in the unsaturated zone. So we have an under pressure, and this is because of the capillary forces. Okay, and these parameters are not constant, but they are functions that depend on the pressure head. So one can read it like this: the larger the under pressure, so to say, the more negative the pressure head, the drier the soil is. And the hydraulic conductivity can be read in a similar way. The higher the negative pressure, the drier the soil, the less conductive. Now, so and this is how this would typically look like. And then we have a full zoo of models how to parameterize these functions. So this is the standard model. It's not the only model. And I want to say some words about it because it's discussed a lot and well known that this model, this standard model, has shortcomings. There are a lot of processes and mechanisms that are not well captured with it. And the same, so we are facing the same as for any two-phase flow model. And there are lots of examples. I just picked some, just examples, and I took them here from the literature and put them all into one slide. So for example, we have trapping of air. Not a lot because the air is really very mobile, but in the capillary fringe where the water table is moving up and down, we have trapping of gas. This is not well represented. This goes into the residual saturations, which are not constant, and so on. We have non-equilibrium. So we have situations where due to redistribution, we have, let's say, the same water content or saturation, but not the same pressure head. So this we have and then we have film flow and corner flow. And in soils, this is quite important for evaporation, also not well captured in the standard models. And then we have these famous instabilities, or the water fingers that you get if you have infiltration into a dry coarse material. No Richards equation will reproduce this. Okay, so there are shortcomings, and it's so there is a lot of work going on how to get better models, how to capture this in a better way. And here is one example. This is a very famous one where the capillary pressure is extended by a dynamic term. And this model has been discussed a lot and is discussed a lot. And it's one of the models that would be able to reproduce the infiltration fingers as an example. There are other models for that, but one example. So there is work going on. Another example is the preferential flow. This is important for soils because we quite often have that. Due to this crack-like structure, we have often infiltration along preferential flow paths. And clearly, this is not captured in a standard Richards model. So there are extensions. And these extensions, there's a lot, are both always based on double domain approaches. Lots of them, double porosity, double permeability, what have you. It's similar to what is done for fractured flow, where we then divide the domain into a mobile and immobile part. And then we have a model here for the mobile part. And we have then the exchange of mass with the surrounding, with the immobile part by whatever we choose here. I chose here a parameterization that I'm used to or like to work with. And this is where we have then these memory functions as parameters that describe the temporal behavior of the mass exchange, if you wish. So there's a lot in this direction. I could here continue. So there's a lot going on. My point is it's on these large length scale questions that I've put up, not established. So this is still the standard model that we use on the large length scales. So we are working with a model that is strongly parameterized. This is clear. And here it's not only the parameters, it's also the boundary conditions. If you think what goes in and out into the atmosphere depends on the plants, on the weather, on the wind, on whatever. So there's a lot of parameterization in there too. And then we have to be aware that we describe with this model typically averages, horizontal averages. Again, so the parameters have somehow to capture this. So to make good predictions, it's clear that these parameters are vital. So we can make good predictions if we have good parameters. And here we have now an issue in the unsaturated zone. And this is because, we need observations to determine the parameters. It's pointless to go into the field and take a sample and measure in the lab because you go 10 meters to the site and it will be completely different. It's not necessarily representative for the large length scale. And so we need other types of observations. And here in the soil, this is really challenging because of the typical observations that we have. Our primary variables are pressure heads. It would be nice to measure pressure. However, this is not done. I mean, we have pressure sensors, but they are not easy to maintain. So it's problematic. It's just typically not used. We can in the soils not carry out pumping tests or something like in aquifers where we would see pressure over a large area. So the typical observation is water content or saturation. And this is challenging because we see it in a very specific way. We see very well the top. So with remote sensing data, we could see water content on the top, but with satellites, very large areas. It's only the top and averaged over very large areas. Otherwise, we have geophysical devices, like here TDR probes. We might be lucky and there might be a lysimeter. But on the large length scales, these are points. So our information is typically point observation. I have to say there's light on the horizon because there are cosmic ray probes and they are developed at the moment and getting more and more established. There's a lot happening in this direction, and that's good because these are measurement methods where we see really a good footprint, 100 meters or several hundred meters, and they go a bit deeper down into the subsurface. But they are not established yet, so I would bracket them out for the time being. Okay. And why this is now such a challenge, I would like to illustrate with two toy problems. So two toy problems generated in the computer, just to illustrate why it's challenging to model given the observations that we typically have. The problem is that the model that I've shown is very nonlinear And to identify parameters, we usually require to see a full range of observations. So from dry to very wet to very dry, if we want to retrieve the parameters. And this is illustrated here with really a toy problem. So I put up a model, a column, a soil, and I have an ideal model now. So I have a parameterization that is a standard one. I have boundary conditions. So I have a groundwater table at the bottom. I have flux of water in and out over the top. And then I assume I have a typical sensor setting. So I have 4 devices in the upper part of this column. And then I compare that to a situation where I have 10 devices which cover the full range from the groundwater table to the top. And then I do in the computer measurements, and everything is ideal. And I take the ideal same model and the ideal same boundary conditions and just want to see, do I get out what I put in? Yeah, so this is all with inverse modeling. And the thing is, I can. I mean, it's really an ideal setting. So one can find the parameters. We do here inverse modeling with acknowledging uncertainties. So we have here distributions of the 4 parameters that we want to estimate, no matter what they are. The point is, we see here our prior distributions in dashed, and they are quite broad because we don't know the parameters. And then we have in this solid lines the true parameters, and then we have the posterior distributions. And if we have 10 sensors and see the full domain, this works very well. We retrieve the parameters nicely. If we have only 4 sensors and see only the top where it's typically drier, we are far off. So we don't retrieve the parameters. That doesn't say that we don't match the observations. We match them very well. It's just in this dry regime, it's not sensitive. So it's not sensitive to these parameters, and therefore we cannot get them. So this is just to illustrate that if we only see the top, it's problematic. The other issue I would like to bring up is that we have point observations because, as I said, we want to predict spatial averages. And what we should see is a representative elementary volume, so something large, but we don't. And that this is a problem, again, I would like to illustrate with another toy problem, very similar. So now my toy problem is a 2-dimensional problem. And I have here a heterogeneous parameter field. In blue is coarse material, in red is fine material. Roughly speaking, here's the structure. And I have, again, a groundwater table, and then I have inflow and outflow over the top. And I know it all perfectly well. I have here a homogeneous model that describes the spatial average. It's parameterized in a certain way so that I can really write it down. I spare you the equation. It's going to fill a page. It's a horrible model, but it's there. Yeah? So it would describe the average, and it has 3 parameters. Okay, and just to convince you that it would represent everything nicely, here's an example of an infiltration calculated with these 2 models. So we start with the red curve, the water content over depth, and this is wet at the bottom, dry at the top. Then it starts to rain, and the blue curve is seen next. So there's the water coming down, it's getting red at the top, and the waterfront's going down, and it's continued to rain, and so the soil gets wetter and wetter from green to pink here. And the solid lines are my upscaled model, my homogeneous one, and the dashed lines are the averaged heterogeneous one. So if I find the parameters, I'm well able to predict. However, now I assume that I have sensors and I see the whole thing from top to bottom. So this is here not the problem, but I see only points. And if I see points, can I find the parameters? No. So this is if I see points. Again, this is from a parameter estimation. I have here my 3 parameters, whatever they are. The red values is what I should find. And my posterior distribution is the blue thing. And I'm absolutely off. So the points are just not representative for what should be predicted. If I had sensors, if I had a chance to see horizontal averages over the whole depth, if there were such sensors, I would be nicely able to retrieve the parameters. But the point is, this is typically not the case. Okay, so these were just examples to illustrate that if we use these models on large length scales to model flow in the unsaturated zone, we are facing a situation that we use models that have model errors anyway, but we have also a big uncertainty concerning the parameters of these models. Okay, and now we want to use these models and do that in the framework of data assimilation. Now I want to say something about data assimilation, what I mean by this. In general, I mean with data assimilation that I want to reduce a model error or model uncertainty by taking observations into account. And we are looking into this in a setting where we want to model continuously processes in the unsaturated zone. Let's say like weather prediction. Yeah, so we want to predict, let's say, water content in the unsaturated zone continuously in time. And we do this by taking into account observations that come in continuously in time. Let's say we have a sensor network somewhere, and so we get these observations continuously in time. And of course, in such a story is not done for the unsaturated zone alone. In this case, the unsaturated zone is part of a bigger system. So we look maybe into a small catchment, and then we are also looking into the rivers or into the atmosphere, and the unsaturated zone is a part. But here I would like to look only at the unsaturated zone. Okay, and now some words about how does this work, or how do we do this with data assimilation. And so this is how it works in a very crude picture. So we have a state, let's say water content, that we want to predict. And we have a model, and so there is a mismatch due to all the reasons that I just talked about, and we should acknowledge this. So we don't have just a state, we should have a distribution for the state. We should acknowledge the uncertainty, and there's a mismatch. And then we have an observation, and here also we have a mismatch because our measurement devices are also not perfect. If I do data assimilation, I try now to merge this and reduce the model error of my model by, in a way, conditioning to the observations. So I build, so to say, the distribution given the observations that I have, and I'm then looking for the best estimate, so to say. And this means if everything goes well, it should look like this. Here's the state I want to predict, and I have a distribution. I acknowledge the uncertainty. And this is my simulated PDF in dashed. I have then an observation. Again, I acknowledge uncertainty. So there's a distribution in the dotted line. And that's the truth, of course, I would not see. But in both cases, I'm a bit off from the truth. And if I do now an update by data assimilation, what I should get is then a distribution for my model that is closer to the observation and has a smaller uncertainty. So I get closer to the observation and I get a reduced uncertainty. So this is how it should work. Okay, and this I want to do now sequentially in time. And that means I make predictions in time continuously, taking observations on the way. And this is how it would look like. So here is my state over time that I want to predict. I need a distribution. I want to acknowledge that it's uncertain and it has an expected value that is my best guess, so to say. And this is with the model progressed in time. And then I have an observation. And now I do this. So I do an update. And with this, I get closer to the observation and reduce the uncertainty. And then I continue until I have the next observation, and so on, and so on, and so on, and so on. Now, so this is how it should work. The question is now, how do I represent this distribution, the PDF, and how do I perform the update? Okay, and this I will now cut very short. What we do here is what many people do. We use an ensemble Kalman filter. And this is a very popular method because it works often quite well and it's not so difficult also to implement. It's a Monte Carlo based approach. And that means the distribution I represent with an ensemble. So I generate an ensemble of states and this ensemble reproduces my uncertainty. So I have an expected value. This is represented by the ensemble mean and the uncertainty is represented by the ensemble spread. And how do I do the update? Here, I will really be short. So this F index stands for my model prediction. And then I get an updated model prediction by updating with something that is proportional to the mismatch of my observation and of my simulated observation. And the proportionality, this is the Kalman gain, and into the Kalman gain go these covariances of the observations, the error covariance of the observation itself, of the modeled observations, and observation and modeled observation states, and modeled states. Okay, and I don't want to go into detail how it is derived. One thing has to be clear, there are a lot of assumptions that are in there about linearity, Gaussianity, and so on. But this is how it's used here. Okay, and one word, I can do this not only having in my state vector my model states, so pressure heads in my case, but also my model parameters. I could also have boundary conditions in there, but the model parameters are for us interesting. So I could keep them also in the state vector and update them with the observations. And in this way, maybe hope that given the observations, I improve my model parameters on the fly, so to say. So I could do this. Okay, and so how would this look in a soil now? I have a soil model, say any model. I have a discretization, so let's say 100 grid cells, so I have 100 pressure heads. And so my state vector has here 100 pressure heads. I have boundary conditions, and here I assume that they are deterministic. Of course, they shouldn't be, but this is here what I assume. And then I have, let's say, 4 parameters, a standard parameterization. And now they don't have to, but they could also go into the state vector. And then I have observations, let's say water content, 4 of them, 4 sensors. And these are my observations. Okay, and now this is how this would then work. Here's my state vector. And now I generate an ensemble representing the uncertainty. And now I progress in time. The states, so the pressure heads with the Richards equation, the parameters, if I have them, with identity, of course. And then I have an observation, there's an update, and so on and so on. And this is how one progresses in time. Okay, so this is how this would look like for soils. And I would like to show now one example. I should say this is the only example I'm going to show with real data. Everything else I'm going to show, because we're looking into the question of uncertainty and everything, is all toy problems in the computer. But I mean, we also work with data, but I'm not going to show it. Here is the only thing where I show real data. So we had here observations from a group in Heidelberg who had a plot instrumented. So they had 4 of these TDR probes. And over a year, we had measurements. And they also had measurements for the rainfall and everything. So we had also the boundary conditions. And then we use this data to try how does the data assimilation work. And then this is how it would look like, for example. So here, what we predict is the water content or saturation over time. And note, this is the observation directly at the location where I measure. So I predict the water content at the point where I have my measurement. And the dots are here my observations. The gray thing is my ensemble, my model ensemble, and the red is the ensemble mean. And here this goes over time. In the first period, there's no observations taken. So this is just running the forward model. And the spread is very large. One does this to get the model into a reasonable state, let's say, with an initial condition. And then this filter starts and the observations are taken in, and what happens is what should happen. The uncertainty is reduced immediately, maybe even too much. And my prediction goes very close to the observation. So one could say this is great, this works well. But as soon as I switch the observations off, here in this time period, there were no observations taken, the model goes completely off. And this goes to show that in this case, it's really data-driven, because if I have no observation, my model does something completely different. So that means my parameters are not good, so are not good, well chosen. And as soon as I have no data, but also most probably, if I'm away from my observation point, I probably do not make good predictions anymore. So just as an example how this could look like. Okay, and now to the question, if we do this now, how do we deal with the fact that we have very uncertain models concerning the parameters and that we have heterogeneous reality that we represent somehow with this model by predicting averages. Okay, and now I should really say what I'm presenting now is Natascha Brandhorst's work. So she did what I'm going to show now. First, the question with the uncertainty. And this is, again, toy problems in the computer. So the toy problem in the computer is this: I generate a reality in a homogeneous setting. So for the time being, I do not want to see heterogeneity. I just want to see uncertainty. So I have something that is completely homogeneous. Again, I have perfect settings. I have boundary conditions that I know. I have the flow going in and out, rainfall, evapotranspiration that come in and out over the top. I have, again, 4 sensors, and I have a measurement of water content. The thing is, I don't know the parameters. Yeah? And now I do data assimilation with uncertain parameters. And we took everything from the tables and tested also different materials. Okay, and then different strategies to deal with this situation that our parameters are uncertain. The first strategy is to do nothing. Yeah? So just take a wrong parameter. So let's say we know what the soil might be. We know that it has some sand, some clay. This you can find in soil maps that are maybe available. And then we go to the tables and just choose a value. But in the tables, you already find a big range, so it's likely that this will be off. So we just use it. So we generate our ensemble. We do not update the parameters, only the states, and all models have the same wrong parameters. I mean, it's not completely unreasonable because we do data assimilation. The reasoning would be to say that the errors that I do are fixed, so to say, by the observations. Okay. The second strategy is to do exactly the same, but acknowledge that I will be off with my model and do a bias correction. And this we did because bias corrections are really used a lot in practice. So we add a bias correction, and the bias correction runs through the filter. The next strategy is to say we acknowledge at least the uncertainty of the parameters by choosing from a distribution. So we give the parameters a distribution and take this into account by assigning to each member of the ensemble a different parameter that we draw from the distribution. We don't update them. The reasoning would be the uncertainty that I have in the parameters is reflected by assigning it to the ensemble, and this will then keep the uncertainty here in my predictions. And again, this can be done in combination with bias corrections. And the third strategy is to say, I have an uncertain parameter, so I give it a distribution, I sample from the distribution, but then I update my parameters on the fly. So I take the observations into account to update also the parameters, to try to get better parameters for the model. Okay, and these are the results. This is quite condensed, but it's all in there. So what we used as a measure for quality is the root mean square error of the water content in the whole column, so everywhere, averaged over a period where we did not have observations. And we tested different materials, and then we have the different strategies in solid. We have without bias correction, in empty with bias correction, because we wanted to see what does the bias correction do. But one can really cut this very short, because in any case and always, the best strategy is to update the parameters. So in a way to optimize on the fly the parameters with the observations. And now one could be tempted to say, yeah, this goes to show that my model gets better and better and better because I'm getting closer and closer to the true parameters. But this was not the case, never. Not in a single case did we retrieve the true parameters. We were always off. But the parameters were the best or the optimal set of parameters for the situation we were in. And maybe if we change the situation from something where it's very wet all of a sudden, it might even be that other parameters are better, and then they would go into this direction, so to say. So it's getting a bit more of a gray box. But if I want to make good predictions, this was the best strategy we could choose. Okay. And now the last point is the heterogeneity. We were also thinking about how to deal with heterogeneity that I don't know. Huh? And this, again, with the toy model, now it's 3D. because I want to accommodate here something heterogeneous. This is a small hill slope, quite steep actually, so we also had overland flow with a small creek where the water is carried away. And the soil is heterogeneous. Here is the parameters in a horizontal cut, and it's not realistic, but heterogeneous. And again, we have boundary conditions, inflow, outflow at the top, and we know everything else. And here is a cut, so we have on the bottom a bedrock, and then come 2 layers of soil. And again, the parameters were chosen from the tables, and they were also intercorrelated according to the tables. We had, let's say, 3 layers with observations at 4 points, so 12 observations, and we were looking at 2 validation points to see how good our predictions are at locations where we don't have observations directly. But of course, this is not what we are after. We are after the average system. So what we want to see is the full system, and we also looked into that. Okay. And we looked now at lots of different things. I want to show you only one thing. So here we also did the parameter updates that always work the best. But we looked into the question, how do we reflect that our soil is really heterogeneous? If we have an ensemble, we have, of course, uncertainty. But do we on top have heterogeneous settings? And in the parameter updates, this is gross, because we have then as many parameters as the model has times numbers of cells. So this is really a lot. Or do we say the heterogeneity is anyway something we have no idea about, so we represent the model as something homogeneous and just keep the variability in the ensemble spread? Okay, and this is to show just some examples. So again, this is here now my prediction of water content at different sensors. So here at a location where I have observations directly, and here where I do not. And here is this strategy if everything is heterogeneous and here homogeneous. Now the colors have changed a bit. So gray is again my ensemble. In black is now my ensemble mean. This is what I would predict. And in red is the virtual truth, so to say, the observation. And in blue, as a reference, is the mean of the ensemble that I would get if I don't do updates. So if I don't take observations into account, if I just run my ensemble forward. Okay, and as it should be, at locations where I have observations, with taking observations into account, I improve my predictions. This is not spectacular, but what is also very clear is if I'm away from the observation at a validation, I make a very poor prediction. So if I look at the black curves, this is my ensemble mean, they are in any case, whatever I do, still away from the reality. And in one case, even if I don't take observations into account, I'm better than if I do. And this is not surprising because there we really don't know. So we really have no information, and therefore, of course, the prediction is poor. But there is a subtle difference, and I think it is important. In case that I have a heterogeneous model, my spread is still large. So this reduction of uncertainty happens then really only at the observation locations. And because my models are structured in a way that when I'm far away, I'm not influenced by this, the spread away from there remains large. So at least I acknowledge that I really don't know much at this location, while if I have my homogeneous models, the model gets really overconfident. The spread is very small. Okay, and the last slide. So what we wanted really to do is predict the total behavior. So here is just as an example, the average water content in the whole model. From which one then we might want to calculate fluxes, but we didn't do that yet. So this is here just the mean, so to say. And again, it's, so data assimilation improves the prediction. And but what I wanted, the point I wanted to make, again, what is here an important difference, if I acknowledge heterogeneity, I keep the uncertainty, so to say, in it, and my truth, so to say, is covered by the spread. While if I don't do this, I'm getting overconfident and the spread gets rather small. Okay, so with this example, I would like to end, and I thank you for the attention. the point I wanted to make here or to bring across is that if we use models for soils, standard models for soils, we should put some effort into thinking of how do we acknowledge the uncertainty that we have in the models and in the parameters and the heterogeneity that we do not resolve in able to make good predictions. Okay, thank you very much.
Thank you. Excuse me. Thank you very much, Insa, for a really nice talk. And I see that a colleague of yours from Stuttgart Times, Florian Dost, has put a lot of questions in the chat.
I don't see the chat.
I bring them up
Yeah,
here
okay.
for you. So starts out, hi Insa, nice to hear you. So you're using Richard's equation on the large scale. Can you lump the more complex behavior into an effective behavior depending on hydraulic head? The continuous, what are the limitations, i.e. how far can you deviate from the scale and boundary conditions of the averaging procedure?
I'm not sure if I get the question, I have to say. So you're asking if I could if I even could apply the Richards equation on very large
Yes.
scales. Is that the question? Because of course, if I theoretically would say, I mean, I could try to upscale the Richards equation and try to derive a model for the very large scale, yeah, and it's very clear I would not, but yeah, like in any model, I guess, if I want to represent averages, it's very likely, or only under very simplified conditions, do I get the same model out, so to say. So if I would upscale Richards equation, I would not end with the Richards equation. I would end with a lot of extra terms that would reflect that I have different time behavior in the different materials, and so all this hysteretic behavior and everything would come into play. So in a way, if we apply that on a very large scale, that's why I said, I mean, we are using with open eyes a model that has a modeling error. And I think if we could manage to pinpoint the model error, it would maybe even be beneficial to use, let's say, extended models. Yeah? So if I have, for instance, a situation where I have, let's say, preferential flow, and so I want to use then a model, one of these double domain approaches or something. If I really have the situation that this happens a lot and this is going to be seen in the observations, of course, I would make better predictions if this is also reflected in the model. The point is, it's only then helpful if I have the observations that allow then again to get back to the parameters. Otherwise, if I have too many parameters, it gets arbitrary. Yeah? And so I mean, I completely agree. We are using models that, I mean, have a lot of mistakes, so to say. So model error is strong. But I think to try to get to capture this or to counteract this by using upscaled models would be a good idea only if the observations that we have allow for that. Then we would be better.
But just follow up here with a question myself that I was thinking of when I was listening to you talk. So you did a lot of, you set up a lot of your own problems. You could validate the approaches, so you knew what the true solution was. But to get a handle on that model error, and you mentioned the dual domain models, for example. So could you not create a test problem which is, say, more amenable to be modeled by a dual domain approach, whether you try to model it with a classical Richards equation with dual domain approach, and you see how that impacts your data assimilation workflow, if your predictions are getting better, because in the subsurface you often won't know which how good or how
Yeah.
far the classical Richards model is away from some more advanced models.
Yes, yes, yeah. No, that's true. One could do this. I have to say we didn't do it, but it was always the plan, so to say, to try these upscaled models. But then when we started off, and especially using real data, we saw that we were always getting into the wrong direction. We were always better in predictions if we use something that is simpler than if we use something that is more complex. But it was always in the plan. But I should say that especially with this non-equilibrium conditions, there's a group in Heidelberg with Kurt Roth who also worked on these things a lot, and they came up, for instance, with a strategy to say, I try to determine the conditions when I know that my Richards model will be poor. And if I know that I'm in such conditions, I just say, I'm not going to do anything here. I'm not going to predict because my model error will be too big. And I start predicting again when I know the conditions are different. So this would also be a strategy.
But could it be that if you have this, you mentioned you had the best model, that's the model that worked best was the Richards equation? Could this be because you're just in an unlucky situation, a lot of the model errors start to cancel each other out because you have a relatively simple model, or do the physics then just not matter?
I have to
Certain
say,
bits
I
of
think the physics, I mean, the physics do not matter so much. I mean, what I should say, I mean, we have preferential flow, that's true, and it's found a lot, but often also not. So if you want to maybe predict, and therefore I was after this large scale. Yeah, so if you want to predict something, I don't know, the flow in a field directly towards plant roots or something, then you would see a lot of this. But if you really just want to see the water getting down and getting then out of the system and getting down, soils are pretty slow. So, um, it's it's often, I would say, not that we have these extremely fast processes. They are there. We have them, and then it's problematic. But often also not. I think then it's much more difficult. I think the error or the uncertainty that you have in the boundary conditions is maybe much more important. So because if you want to know how much is getting out, you need to know how much the plants take out, and you have to know how much is evaporated. So you need to look at the coupling to the atmosphere, and there's a lot of uncertainty in that. And that would probably in normal situations just beat this if I have at some points very fast behavior. So.
Thank you, Insa. I'm coming back to another question that Florian had, and again, so it's a two-part question. It says, with respect to slide 19, how many horizontal points would you need to be able to catch the parameters? And
Oh, that's a mean question. I didn't try that.
and he
Okay.
said, would it help to change the location of the observation points in time? Practice is
Yes.
maybe more difficult, but on the computer you can do a lot.
Yeah. Or Florian has ideas, huh? So I, I have to say I didn't test this. If you wish, I mean, what I did with the horizontal average, I took as many points as I have had grid points. I don't remember how many they were, but I really just took the horizontal average and we did not try if I had another row, if this would already be sufficient, or if I had 3 rows, this would be sufficient. I mean, I'm just guessing, but I mean, because everything is artificially created, one can easily maybe say what's going to happen. I have a correlation length in the field that was generated, and I guess I would have to cover the correlation length. So I guess if I had a sensor row that covers, let's say, 3-5 correlation lengths, that should be fine. I should maybe I would not have to see the full field. I just would need to see several correlation lengths. Yeah.
Mm.
And in
Yeah.
time, good question. I don't know, but I guess yes. I guess this would help. One could even say we take temporally average observations and try to get them into the as an observation that we want to match to get the parameters.
Thank you. Thank you again, Insa. I don't see any further questions coming through.
I do
Here
have a
from
question.
yeah,
Can I ask a
Julien, you
question?
go ahead. Yes.
I guess I'm surprised that in a presentation about data assimilation and prediction, we didn't talk about machine learning. So is there a place for machine learning in this? Is this a competition for you, or can it be included to help?
Machine learning is you can use it everywhere. Huh? I don't know. Um, I don't know. I mean, in this procedure, I'm just trying to think where would I replace something with machine learning? Do you mean with the predictions? If I have a lot of observations that I
Yeah, I
want
think
to make
eventually I would expect
instead of
the network to converge towards the right prediction after a while. And um,
yes, I guess that is yeah, maybe that's true. Yeah. So if I have a lot of observations, a long history of observations, that's true. Maybe I would, but I mean, okay, if I had a lot of observations and I use then machine learning instead of any physically based model or model that at least claims to be physically based, and use machine learning to do the predictions, the point is I would need to see everything, right? Um, because I cannot extrapolate. So I would need really observations. I mean, the point here is that I don't see everything. Yeah, if
yeah,
I only have, I can imagine that if I only am only after the very top. So I just want, let's say, I'm just after weather predictions. So I just want to see the state at the very top of the soil surface, and this I can really see well with satellite data or something. There, I agree. Then maybe one day one will use machine learning to make predictions. But the point is, I want maybe also to see a bit further down because I want to estimate the other water fluxes too. Huh? And there I don't have I mean, that's then maybe the strength of something that is at least a bit physically based. Yeah, so that uh, I have a handle to infer from what I see to what will happen further down. And as long as I cannot see this properly, I don't know how a machine learning model would then beat other methods.
and we can do physics informed machine learning network. I guess the question is the amount of data we actually
Yeah,
need to
yeah,
predict.
yeah, yeah, yeah.
Maybe starting with the homogeneous case. I'm still processing the fact that we are not getting the coefficient back in the homogeneous. So simple and yet so complicated. Maybe there is something to be put in there.
Yeah, yeah.
So I don't see further questions coming through. Here, Florian commented again. He's been very active, and I think we discussed this. He said, at what point could you just bin the physical model and let machine learning do all the predictions? I think you answered that question already.
No,
Insa,
I
you said
think we are not there yet.
we're not, and I don't think we will ever be there. And I think Florian may have asked that sort of rather cheeky question. And I would be surprised we would ever get there because we simply can't measure
No, we
enough
don't see, we
data.
don't, and that's exactly the problem. Yeah, otherwise we could put up nicer physically based models and could put in all these extensions and everything if we could see everything. Yeah.
So let me thank you again, Insa, for a really nice talk, and especially considering that's a public holiday today in Germany. So you made the way into your office to give that talk. I hope the weather was not that good that you're sort of missing out on some
No,
really
I don't miss
fun
anything.
outdoor.
The weather is poor.
Okay, so thank you very much then for spending your afternoon with us, in your free afternoon with us, Insa. It's really greatly appreciated. Julian, over to you for some final comments announcing our next speaker.
Yes, so also I would like to thank you, Insa. That was really enlightening. It made me not to think, especially about that homogeneous coefficient that is not retrieved. I will have to process this a long time. Yes, this is time to say goodbye. So next week we will be welcoming Dr. Naomi Bonus from Stanford University. And in the meantime, stay safe, stay connected, and stay happy. Goodbye.
Thank
you,
you.
everyone. Bye-bye.
Bye.